Hello everyone, this is Sir Aris. Today we'll talk about a continuation of evaluation of definite integrals using residue theorem and also the residues at infinity. We consider the Laplace transform of function f of t is equal to the integral from 0 to infinity of ft times e to the minus pt. Um, we'll call the Laplace transform the resulting function as f of p. P is the quantity here. Suppose p is a complex number, say z, so that we will have fp is equal to integral from 0 to infinity of ft. Um, Hold on. If p is a complex number, let me write that first here. So that this is from 0 to infinity of ft e to the minus x plus iyt dt. So this would be um, integral from 0 to infinity of e to the minus xt times ft times e to the minus iyt dt. With the condition that the real value of p, which is x, is greater than some real number. The simplest case, um, x greater than 0, so that this will turn out to be convergent as t approaches infinity. So here, if you recall Fourier transform, if you want to transform fx into g, you just use this formula here. You can also reverse transformation. We use this up to this 1 over 2 pi here. This f of x plus iy, or fp, is similar in form to this. Okay, you have this I e to the power of minus iyt, same with this. Okay, except that, so for here or this alpha is equivalent to this y, t is x, so this t here, yeah, this dt is correspondent to this. So t corresponds to x. This corresponds here. This e to the power of minus xt would correspond to this term here. Okay. So this would also correspond to this g um, alpha. Okay. So if we define phi t as e to the minus xt times ft if t is greater than 0, 0 if t is less than 0, then we have phi t, which is our fx here, or um, this is our phi t. So this here is our phi t for t greater than 0. That would then be equal to this fx here. Since we don't have that normalization constant here, 1 over 2 pi, we can put that here also. So 1 over 2 pi integral from 0 or minus infinity to positive infinity. G would be our f of x plus iy. Okay, that g corresponds here. Um, Alpha is y, so we have e I y t dy. Okay. For t greater than 0, we have e to the minus xt ft equals phi t. So ft is just e to the power of xt phi t. So if you write our ft, that would be actually let's I will just continue here. So ft would just be um which is this phi t here. Okay. Oh no, ft is this phi t times ext. So ext phi t is this integral. So that's 1 over 2 pi integral from minus infinity to infinity of fx plus iy e I y t dy. Is that right? Okay. So this is equal to 1 over 2 pi. We put this inside the integral minus infinity to infinity of fx plus iy e x plus iy times t dy. So in our case, we have set x a constant. So if z is equal to x plus iy, dz is just I dy. So if you set this to z, this z, dy to dz over I, then you have ft equals 1 over 2 pi I integral from negative infinity in complex number. It means that if um, x is a constant, let's say x is a constant, suppose x equals c, then it becomes c minus I infinity here and c plus I infinity. It's just like c is just in the complex plane, c is x is fixed at the value c. So we go from negative infinity along the y-axis to positive infinity. The integrand is fz e z t c z d z, working for t greater than 0. This is called the Bromwich integral. This is relevant because if you want to solve this contour integral here, um, the value is just equal to 2 pi I times the residue. So it means that um, it can be shown. So it can be shown that ft is equal to this or 1 over 2 pi I times 2 pi I times the residue of this. So 2 pi I cancels, so it would be sum of residues of f z e z t at all poles. So which means that if you know the form of fz, you can easily find the inverse Laplace transform using the Bromwich integral. For example, find the inverse transform of fp. So in this example, we first find the poles of fz e z t. So if you write f z e z t as, so p we replace by z, we multiply everything by e z t. So you have 5e zt divided by z plus 2, z squared plus 1. Z is a complex number, so you can also write f e z t over z plus 2, z plus I, z minus I. In this case, there are three simple poles at z equals negative 2, z equals I, z equals minus I. For the residue at z equals minus 2, you have our notation r at minus 2 equals 5e minus 2t. So we multiply both side, numerator and denominator by z plus 2, and then set z to minus 2 over um, minus 2 plus I and minus 2 minus I. This becomes 5e minus 2t over this is 4 plus 1, okay, equals e to the minus 2t. For the residue at z equals I, you have ri is 5e it divided by um, multiply numerator and denominator by this. So you have I plus 2 and I plus I. So that's 2I. Okay. This becomes 5EIT over I times 2I. That's negative 2 plus 4I. Okay. For the residue at z equals minus I, so r at minus I would be 5e minus it, so you have minus I plus 2, and here's that. Here we set minus I plus I minus I minus I, so negative 2I. This becomes 5e minus it um, minus 2I. So this becomes minus 4I, or actually minus 2, minus 2I minus I. That's plus 2I squared, so minus 2 minus 4I. Okay. Finally, we can write ft as the sum of residues of f z e z t, which means this 3 here, e to the minus 2t plus 5ei t over minus 2 plus 4I plus 5e minus it over minus 2 minus 4I. Okay, we keep this, we combine this two. You have, let's say, we have minus 2 plus 4I minus 2 minus 4I, so 5EIT minus 2 minus 4I plus 5E minus IT minus 2 plus 4I. Simplifying, you have um, here 5 times minus 2, that's 10. Actually, we can factor out negative 10. So minus 10. So that here you have 5 uh, EIT times 2. Okay. EIT plus this and this. You also factor out E minus it. Okay, plus we have factor out 2, so we're left with 2I here. 2I e it, this one plus, or actually we factor out minus 10, so this should be minus e minus it. Okay, um all over. So for this 2, minus 2 times minus 2, that'd be 4. Okay, plus 16, or actually it's supposed to be minus 16 I squared is negative 1, so plus 16. Okay, so this 20, so minus 10 over 20 EIT, that's 2 cosine of t plus 2I, and this one is sine, so I 2I sine of t. Okay, so if you add this, which means that the final answer is e minus 2t. This is 10 times 2 is 20, so minus cosine of t. Okay, I times I is minus 1. So you'll have here plus 2 sine of t. That would be your inverse Laplace transform. So let's proceed to the point at infinity. To investigate the behavior of a function at infinity, we replace z by 1 over z and consider how the new function behaves at the origin. For example, if you have z squared at infinity, 1 over z squared has a pole of order 2 at the origin. So z squared is a pole of order 2 at infinity. If you have e 1 over z, z is analytic at z equals 0, therefore e 1 over z is analytic at infinity. To find the residue, we replace z by 1 over z and work around the origin. So we use two variables, capital letter z takes on values near infinity, small letter z takes values near 0. The residue at infinity is defined using the residue theorem. So if you have this formula, this equation, equals 2 pi I plus residue at z equals infinity. So this is what we need to find. So if you can evaluate this, we can find the residue. C is a closed path around a point at infinity, but enclosing no other singular points. Here we traverse C counterclockwise to enclose the area around infinity. So this, just to be clear, this is both x and y. Infinity is somewhere far. If this is our contour, that's our C. If we traverse counterclockwise, it is always that our area of interest is to the left of our arrow, so it would be this. Okay, but if we traverse clockwise, the left is outside the circle, which would now include infinity. If we set z equals rei, capital letter theta, it means that we are going in. So if it's counterclockwise, we are decreasing theta. Applying change of variables equals 1 over z. So dz is negative 1 over z squared dz. 1 over z is 1 over re. Put a negative here. So if we traverse counterclockwise, it means that we are still decreasing the value of capital letter theta, but increasing this small letter theta here. So we have counterclockwise, although we're decreasing capital letter theta, and we call the contour C prime. So we have C prime negative 1 over z squared f 1 over z dz, and 2 pi I, that's still our formula here. We just changed variables. So if you have this, if you focus on this, then you can also find the value of this using the residue theorem is just the residue of this function times 2 pi I. And if you cancel out 2 pi I, the residue, this residue, is just the residue of 1 over z squared f1 over z at z equals 0. For example, suppose z is analytic at the origin, so that 1 over z is analytic at infinity. Find the residue of fz at equals 1 over z at z equals infinity. So we uh, need the residue of 1 over z squared f1 over z at z equals 0. So 1 over z f1 over z, that's simply 1 over z squared, z squared times 1 over z of this is z. 1 over z, that's z, equals 1 over z. Okay, so the residue at 0 is just equal to 1. So we set multiply numerator by z, uh, yeah, numerator by z and z cancels. So r at 0 is 1. Therefore, the residue using the formula residue of f z, capital letter Z, at capital letter Z infinity is just equal to the negative of residue of 1 over z squared f1 over z, small letter, at z equals 0, which is just, this one is 1, so the answer is minus 1.